It's great to be here. Excited to share with you my journey reverse engineering a Bluetooth-enabled blender. So this is the NutriBullet Balance, and it is a Bluetooth blender that is primarily controlled through an app on your phone. So the app on your phone lets you get like the weight of the built-in scale and measure ingredients, as well as pick what blend setting you want to use, so like a sequence of blend on for a bit, then off. And it's a nice blender, but there are some issues I had with it. So the minor ones were that it doesn't remember what the last blend setting you chose is. So each time you have to open the app, pick the blend setting again. And the pulses, it doesn't quite turn on and off enough to dislodge food that is stuck in the bottom of the cup. So it'd be nice if you could customize it a little bit. But then I got a new phone and the app stopped working. So on the left is my new iPhone, and on the right is my iPhone 6 running iOS 15. And as you can see, my new iPhone cannot find the blender, whereas my old one is able to find and connect to it just fine. And if we expect the manufacturer to do something about this, well, the last update was 4 years ago, adding iOS 13 support, so we're on our own here. Now, my setup looks something like this. So I had my phone, the blender, and then they're wirelessly connected over Bluetooth. Maybe not outdoors, but you know. So since this is a connection-oriented protocol between the blender and the phone is acting as a Bluetooth central. And it basically is scanning for devices that advertise their presence, and then it can connect to them. The blender, on the other hand, is acting in the role of a peripheral, which sends out advertisement packets to nearby devices that might want to connect. So I want to know what data is getting sent between them, and my first thought was the easiest thing to do is just install an app on your phone. So I found an app called BLE Scanner, and then there it appears right on the list, so I can connect to it, and then I get a whole bunch of information. Sorry, that's kind of small, but as you can see, it has like a device identifier, and then in the advertisement it was broadcasting, it has some information like, I provide these services, and this is my name, so the app can identify what blenders are relevant for it to use. Going farther down, we can see that it also sent over what service it supports. So there's a few custom services with 128-bit unique identifiers. And farther down, there's a few standard Bluetooth-defined ones like device information that have a 16-bit identifier. Diving into one of these services, we can see that there's a bunch of values called characteristics. And they also have a unique identifier. And they also have properties, such as the ability to read them, write to them, as well as notify, which is basically the server device sends you value changes instead of you having to ask for them. In addition, if it's readable or notifiable, then you'll see a value for that characteristic. If it's writable only, then, well, you're out of luck. And you also have a number of optional descriptors, which one of the primary use cases for them is so your phone can say, hey, I want you to send me notifications or disable sending notifications. So this was enough for me to find out what some of the readable characteristics were, like the scale weight, but for the writable ones, like saying the blend profile, no idea what to choose. So I'll have to get that somehow else. What I ended up with after using that app was a device profile that looked something like this, where I have a list of services and then the nested characteristics that each of those services supports. This hierarchical ordering of information is called GATT, the Generic Attribute Protocol, and is built on top of the Attribute Protocol, which will become relevant later. But essentially, the Attribute Protocol is taking that hierarchical data and then mapping it to a flat table of attributes with 16-bit handles identifying where in the table they are stored. So I want to capture what data is being written to the blender, so I need a way of intercepting the packets. So the first thing I tried was taking an NRF52 development kit, installing BLE sniffer firmware on it, and then intercepting the wireless transmission between the two devices. And this worked. I was able to capture the packets in Wireshark. However, there are some downsides. Getting all the firmware installed on the sniffer, installed and setting up software on the computer was a bit of a hassle, and is a bit finicky in terms of distances between devices when signal gets weak. In addition, you have to buy external hardware, which isn't the greatest. So ideally, I'd like to be able to just take my phone and plug it directly into the computer. So turns out, inside of your phone, it looks something like this. You have the Bluetooth controller, which is talking to the radio and handling low-level aspects of Bluetooth. And then you have the host processor, which runs your application, as well as parts of the Bluetooth stack, like the GAT and attribute protocol layers. And there's communication between them that happens over a link called HCI. Yeah? Oh, thanks. Or the host controller interface. So both Android and iOS let you snoop on the communications happening here. So this is another place we can intercept what's happening. So on iOS, you have to go and get a configuration profile from Apple to install it. But then once you do that, you can then hook it up to your phone using a cable. Using the macOS packet logger software, you can then get all the information it's sending and receiving. So here, I captured the initial connection to the Blender, so I get the list of services and characteristics it advertises. And then after a little bit, once we're connected, I then step through each individual blend setting profile to capture the write request that my phone is sending out. After capturing that information, I can then stop the recording and then go up into the filter menu, select attribute protocol, packets getting sent from the device, and narrow down the list. After narrowing down the list, you can zoom in and see that it has captured the characteristic that's being written to. So this is something I'll need. Now I know what I need to write values to control the Blender. And it tells me what value is written. So I mentioned the attribute protocol before and starting sniffing before connecting to the device. So if you don't do that, then you only get the 16-bit attribute handle. You do not get the characteristic that you need to write to in order to control it. So after getting all these values, I put them into a table like this, and then lay them out with the blend time. And right away, we can see that the standard blend, which is basically just on for 45 seconds, is only 2 bytes. So let's try splitting everything up into 2 bytes and see what it looks like. And we can start to see some patterns emerge. So especially in the second byte, you can see that when it's always on, that's just A0. For the other ones, there's an alternating pattern of A0 bytes mixed with null bytes. So since the blend profile turns on and off, this is likely the motor speed. If we take a closer look at this first byte, if we convert B4 to decimal, we get 180, which is 45 times 4, or the blend time in quarters of a second. To confirm that, we can take the super blend profile, convert the first byte for each of those pairs into decimal as well, add them up, and we get 204, which is the blend time in quarters of a second. So with that, I was able to write a web page using web Bluetooth, and then we can see the Blender shows up, connect to it, and then in a moment it will synchronize, and we start getting characteristic values that are readable. You can see that we're getting a scale weight now, and as water gets poured in, we're getting notifications about the weight increasing. Then I had a drop of blue food coloring, so it looks a little bit more interesting, hopefully. Take the cup off and prepare it. Yeah, time remaining, you can see it says 45 seconds for the standard blend profile I gave it. And then let's go create a custom profile. Might be hard to read, but the first step is running for 12 quarters of a second, 3 seconds at a slow speed. Then next it's going to run for 3 seconds at a slightly higher speed. Then it will take a 2-second pause before finally going for about 2 seconds at roughly the maximum speed supported. So I can then save the profile to send the packet over to the device. And then you can see time remaining is updated to 10 seconds. And I'll put the cup in and twist it to start the blend cycle. So now it's running for about 3 seconds slow. Now it should speed up here, and it's going to pause in a second, and then full speed for 2 seconds. And now it is done. We have the perfect blend setting for blue water. All right. So this is available on GitHub. If you want to check it out, play around with it. If you happen to have a NutriBullet, you can try it out too. Scan the QR code if you can. Otherwise, github.com/nightlark/NutriBullet. And thank you. You can find me on Discord and social media at @rmast.